And in two-dimensional dynamics is very boring. What happens in two dimensions, when you walk on a table, everybody has to have unique future, unique past. So how you can do it? You can get here and just fall off the table. You can have endless, infinite lines. Or you can maybe spiral forever toward a fixed point, or be at a fixed point. Or you can have a circle on a table, some kind of loop. And that's it. So that's a book of Strogatz. So if you ever take the first course in nonlinear dynamics, you'll learn how to do two-dimensional stuff. So so you can make it kinky and relaxation oscillators, neurophysiology, etc. But it's so simple that you get very simple dynamics, even though in 5 dimensions. So that's why you must use the symmetry if you have it, because if you were just running a computer, you would never realize that there is totally boring dynamics in this case. You can just run 5-dimensional systems. So what do I know? Yes?
People find my 3D flows are very boring.
Yeah. I mean, they're bread and butter for lots of people, but in 2D flows, you cannot have a chaotic behavior, because to get a chaotic behavior, you should be able to, kind of cross. You should be able to stretch and fold, come close to the same point. In 2 dimensions, you can't do this, because the deterministic equation has only one past and one future, and there is no way to kind of come back and cross over and start mixing stuff up. That happens only in 3 dimensions. So Lorentz attractor was invented to illustrate it. It's 3-dimensional because it's the lowest thing, and Rosslare attractor, this is the simplest example. Back to 2 dimensions. In 2 dimensions, we have a 2-dimensional state space. So M is x1 and x2. You start someplace, and you have a 2-dimensional law that says the law at each point is given by a vector field. You're used to harmonic oscillators. So harmonic oscillator is a special case where this is called Q and P. So that's the simplest example. And for harmonic oscillators, you remember that you only get circles as solutions. But if you have, that has to do with symplectic invariance of that problem. But in general, what can happen is either nothing happens, so you have equilibrium, or you go someplace, and after a short time, finite time, you come back. But this could look terrible when you plot it and compute it. It could go very, very, very fast, and then not move at all, and then speed up, etc. It doesn't look like a circle necessarily. Relaxation oscillators that you use in biophysics or like that. But you come back. Now, the one that's inside cannot go out because it would cross this trajectory. That's not allowed. Every point has unique past and future. So you can't cross. So what can it do? It can make another loop, or it can maybe shrink, but it can't cross itself. So maybe it can go to, it can be a long thing, but it can be just a spiral going to another equilibrium. So inside, nothing good can happen. There can be just small loops or points as asymptotic behaviors, one-time behaviors. But the system might be open, so maybe if you start here, you go off to infinity, and your path is in infinity. So these are all the behaviors you can have in plane. There's nothing else.